Hello dear students, you are all most welcome to today's chemistry class in this Edusat educational channel. Today we will be continuing with the same topic, that is the D block elements. Before proceeding to complete the topic today, let us have a quick recap into previous class discussion, what we had discussed in last time to refresh your memory. In the last class we had discussed introduction means definition, transition elements, why they are called as transition elements, D block elements are called as transition elements because the properties are intermediate between S block and P block. The valence cell and the nearest inner cell, that is penultimate cell, both are incomplete. Third one was 0. They have partially filled d orbitals. Second classification, the d orbital element, that is transition elements, are divided into 4 series. First transition series, that is 3D series, second transition series 4D series, third transition series 5D series, and a fourth transition series 6D series. First transition series starts from scandium to zinc, second yttrium to cadmium, third from your lanthanum to mercury, fourth one is from actinium to ununbium. Then we discussed about electron configuration. The general electron configuration was your n-1 d1 to 10 and ns1 to 2. And we also discussed why electron enters into ns orbital first, then n-1 d orbital. And then we discussed about the atomic size. We also discussed in detail how the atomic size do not vary in irregular order. It decreases up to manganese, then remains almost constant, then towards end it increases. Then also ionization energy we discussed. The ionization energy also do not vary in irregular order, it is a very irregular order. And also I had given you a mnemonic how to remember the ionization energy order. Then oxidation states, transition metals, so variable oxidation states, variety of oxidation states. It is because of a participation of both n-1 d and ns electrons in bonding. Both of them participate in bonding, that is why they show variable oxidation states, variety of oxidation states, and that oxidation states ranges from +2 to +7. And at the highest oxidation state they exhibit oxidizing character, and at the lowest oxidation state they show reducing character. So many things we have discussed. So in today's discussion we have very important properties: density, melting point, colored compound formation, magnetic character, catalytic property, interstitial compounds, alloy formation, everything we will discuss in today's class. Let us have a discussion about the density. So, you know, density means mass by volume. On moving from scandium to zinc, variation of size is not as much as we are expecting. Size does not vary as much, but mass increases. Since density equal to mass by volume, because of increase in mass dominates over size. So, density gradually increases from scandium to copper. But in case of a zinc, here size dominates over mass. So, the density of a zinc is lower than copper. This is the only difference. Otherwise, there is no major difference. And again, on down the group, if you move down any group, the density gradually increases, because again here the mass factor dominates, right. So, density along the period increases, down the group increases. Next is melting point. You know, the melting point of metals depend upon the metallic bond strength. The metallic bond strength means the force of attraction between the cornel and valence electrons. The positively charged metal cations are called as cornels, and valence electrons, that force of attraction is called as your metallic bond. And if the force of attraction is very strong, then metallic bond is very strong. And if metallic bond is very strong, obviously melting point will be high. It is a natural region, it is obvious region. And also the metallic bond strength also depends upon number of unpaired electrons, because if an atom has, metallic atom has a more number of unpaired electrons, and its neighboring atom has also more number of unpaired electrons, in addition to cornel electron attraction, there is a possibility of overlapping of half filled orbitals between the neighboring atoms, and that covalent bonding adds to the strength of a metallic bond and increases its melting point. On moving from scandium to zinc, up to manganese, you see up to manganese, up to chromium, you see number of unpaired electrons gradually increases. So, in case of chromium, you know the electronic configuration is 4s1 3d5 means all the d orbitals are half filled and 4s is half filled means it has a maximum number of unpaired electrons, that is the 6 number of unpaired electrons. So, in addition to normal metallic bond, Cornell electron attraction, chromium has capacity to make additional maximum number of covalent bonds with its neighboring atom. That is why chromium has a highest melting point. So many times it has been asked in the examination, why chromium has a highest melting point among 3D series elements. Only because of it has a maximum number of unpaired electrons, so it has a greater possibility of making maximum number of covalent bonds with the neighboring atoms. That is why its metallic bond strength is very high. So that is why its melting point is very high. But if you will be surprised, its neighboring atom manganese, it has also D5 configuration, it has also more number of unpaired electrons next to chromium. इसके पास 5 unpaired electrons है, लेकिन its melting point is lower than chromium and iron. दुर्भाग्य की बात है. देखिए इसके पास 5 unpaired electrons है. So it is supposed to make more number of covalent bonds with the adjacent atom, but its melting point is lower than chromium and lower than iron, but it should have higher than iron. Of course less than chromium, वो बात ठीक है, लेकिन आयरन से तो ज़्यादा होना चाहिए ना, लेकिन आयरन से भी कम है. It is only because of its simple lattice structure. Only because of its simple lattice structure. So the melting point varies irregularly, very zigzag manner, very funny manner. You see how the melting point varies. You will be surprised to see this is scandium, this is your chromium, then it is your manganese, here it is manganese, this is scandium, this is manganese, again it increases to iron, then decreases to zinc. From the diagram, now you must be clear, the zinc has the lowest, obvious reason. Zinc has a fully filled d orbital, so it cannot make any additional covalent bonding with its neighboring atom. It has only normal metallic bond, Cornell electron interaction. Because of a large size kernel, the attraction between kernel and electron is weak. So that is why zinc has a lowest melting point in this series. This is manganese, this is chromium, chromium has the highest, this is manganese, this is iron. So manganese has a lower melting point than its neighbors. Exceptionally, it is exceptional case. But again it increases up to iron, then decreases to zinc, because after iron pairing of electron takes place, number of unpaired electron decreases, and with a decrease in number of unpaired electron, metallic bond strength decreases. That is why the melting point decreases. Melting point or boil point decreases up to zinc, and zinc has the lowest. Okay. Now next is magnetic property. D block elements and their compounds are mostly paramagnetic. What are paramagnetic substances? Paramagnetic substances are those, if you bring an external magnet to that substance, near to that substance, that if that substance is slowly attracted towards that external magnet, then it will be called as paramagnetic substance. Right. So most of the transition metals and their compounds are paramagnetic. It is only because of presence of unpaired electrons. Remember, only presence of unpaired d electrons in their penultimate cell. The number of unpaired electrons, suppose one electron remains unpaired. You know, electron has two kinds of motion. Around the nucleus it has orbital motion. Because of orbital motion, it creates a magnetic field, and that magnetic field has a magnetic moment called orbital magnetic moment, right. At the same time, the same electron has also spin around its own axis, and because of that spin, it again generates another magnetic field that is called spin magnetic field, and it has a moment that is called spin magnetic moment. That means same electron produces two types of magnetic field at a time because of its different motion. But remember, when electron is present alone, so it can show two types of motion, it can produce two types of magnetic field, and the resultant magnetic field will be the vectorial addition of the two magnetic field moments. But when as electrons are participating in bonding, because of bonding, its orbital motion is affected. Its orbital motion is affected. So, the orbital contribution towards magnetic property, orbital contribution towards magnetic moment decreases. The spin motion only continues. After bonding, spin motion continues, and the magnetic moment is created only because of a spin motion. And there is a formula, how to, this is called spin only magnetic moment for 3D elements. It is only spin only magnetic formula, spin only magnetic moment, mu s magnetic moment is equal to square root of 4s into s plus 1. S is the total spin quantum number. So, if n number of unpaired electrons are present, then there is a formula mu s equal to, you put this direct formula, root over n into n plus 2 Bm. Bm means Bohr magneton, n means number of unpaired electrons. It is only spin, the magnetic moment, that is the magnetic character inside that substance is only created because of a spin motion. That means the substance is already magnetic. When external magnet comes, because of a magnetic interaction, that substance is slowly attracted. If external magnet repel that substance, then it will be diamagnetic. So, it is a paramagnetic, and I am giving a formula, a trick how to write it directly the magnetic moment on the basis of a number of unpaired electrons. Remember, if number of unpaired electrons is 1, so mu s will be equal to root over 1 into 1 plus 2 means root 3. So, it is 1.73. So, you will find difficulty in finding the root over, but here is a trick. Remember, if n is equal to 2, mu s will be 2 point, it is 1, so 1.73. Remember, 1 means 1.73. If number of unpaired electrons is 2, so spin only magnetic moment will be 2.87. 2 means 2.8 above. If n is equal to 3, so mu s will be 3.84. If n equal to 4, mu s will be 3.90. If n equal to 5, mu s will be equal to 4.90, it is 5.92. So, if n is 5, it must be 5.9. 4 means 4.90, 3 means 3. If you do not remember exactly, then you just simply write, if n equal to 3, then you can write mu s equal to 3.87. Okay? In this way, you can write the magnetic moment on the basis of a number of unpaired electrons, right. So, this is the trick. Here you see in cobalt 3, you will be asked what is the magnetic moment of COCl3. COCl3 means the oxidation state of cobalt is +3. +3 means n equal to 4. n equal to 4, what is its magnetic moment? N equal to 4 means it will be 4.90 Bm. Simply सीधा लिख देना ये बात, सीधी से लिख देना, कोई जरूरत नहीं कि कैलकुलेशन करनी, कोई जरूरत नहीं. यू जस्ट राइट द वैल्यू डायरेक्टली, यू विल गेट आंसर. ये एंट्रेंस के लिए बहुत इंपॉर्टेंट फॉर्मूला है. तो इफ n इज 5, 5.96. In case of ferric, n is 5, what will be mu s? It will be 5.92. And in case of Cu2 plus, n is equal to 1 because only one unpaired electron. You have to calculate the number of unpaired electrons, not number of d electrons. नंबर ऑफ अनपेड इलेक्ट्रॉन्स पहले फिलअप करना पड़ेगा आपको डी ऑर्बिटल के अंदर में इलेक्ट्रॉन को एक एक करके रखना, उसके बाद पेयरिंग करना, लास्ट को कैलकुलेशन करना कि कितने अनपेड इलेक्ट्रॉन्स है, उसी को हिसाब करते हुए आपको ये वैल्यू पुट करना है. ठीक है. नेक्स्ट इज योर colored compound formation. Transition metals are making colored compounds either in a solid state or in a solution state. Most of the transition metal compounds are colored either in a solid state or in a solution state. Okay? We will discuss it in detail. You know, the colored compound formation is the most important characteristic property of transition metals. Most of the transition metal compounds or complexes are colored either in a solid state or in a solution state. For example, anhydrous copper sulfate, simple copper sulfate CuSO4 is colorless, white color powder. The moment you put it in water, its solution becomes deep blue color. So, the color may be in a solid state or in a solution state. What is the reason behind this color formation? Not all transition metals compounds are colored. What are the reasons for this color? There are four reasons. There are four reasons behind the color compound formation. There are four reasons. Number one, DD transition. Let us discuss one by one. The four reasons are there why transition metal compounds are looking colored. Number one, DD transition. DD transition is number one. Number two, your charge transfer phenomenon. Charge transfer phenomenon. Charge transfer phenomenon. Third one is your polarization of anion. Polarization of anions. Or fourth one is maybe crystal defect. Crystal defect. Due to these four reasons, transition metal compounds are colored either due to this region or due to this one, due to this one, this. But for DD transition, what is the requirement? The transition metal compounds or complexes must have to have D1 to D9 electrons. They cannot have, if D0 is there or D10 fully filled or vacant, they are colorless. Colorless. DD transition means when you have, you see it is called crystal field splitting. You have 5d orbitals which are degenerate. When they form complex, the d orbital splits. The d orbital splits into two sets. One is called T2G set, another is called EG set. EG set contains dx square minus y square and dz square orbitals. Here you have dxy, dyz and dzx orbitals. It is called triply degenerate orbital. And the energy difference is called as crystal field splitting energy. When you provide energy, equal to crystal field stabilization energy, the unpaired electron, the d orbital has unpaired electrons. The unpaired electron on observing the radiation from sunlight, this is sunlight, undergo DD transition, that is from one set of d orbital to another set of d orbital by observing the energy equivalent to crystal field splitting energy. And go to excited state. Since excited state is unstable, so it returns back, and emits energy that has a particular color. So the substance looks this emitted color, not absorbed color. It might have been observing a particular color radiation, but the which color it will look? The color which it emits, it will give you that color. That is called complementary color. So, here is a beautiful Munsell's circle to see which color is complementary of which color. Means you see orange blue O B Y V G R. Remember these three pairs O B O B C O B C को हटा दो O B Y V and G R. G R means green and red are complementary color. Means if a substance, if a transition metal compound absorbs red color, if it absorbs red color, it will emit green color. Then the substance will look green color. Means whenever a transition metal compound looks green color, means it emits green color, means it absorbs red color. When a transition metal compound looks blue color, means its complementary color is your orange, means it absorbs orange color, it emits blue color and it looks blue color. So, here you see absorbed color, absorbed color, absorbed color and a observed color, means complementary color. Which color is observed and which color it will look. When it absorbs green color, it looks red. If it absorbs red color, it will look green. If it absorbs yellow color, it will look violet. If it absorbs violet color, it will look yellow. If it absorbs orange color, it will look blue, and if it absorbs blue color, it will look orange color. So, any orange color substance means it emits orange color, means it absorbs blue color. So, this is a d-d transition. It is only possible if a transition metal contains d1 to d9 electrons. Okay. On this basis, you see if any transition metal has a d0 configuration, means there is no electron in d subshell like scandium plus 3 cation in scandium chloride, it is colorless because there is no d electron present. So, no d-d transition is possible. So, it is colorless. Titanium dioxide, similarly titanium dioxide, it has a d0 configuration, d0 oxidation state is plus 4, means it has lost all the electrons, again it has a d0, no d electron is present. So, it is colorless, right. Cu2Cl2, Cu2Cl2, you see copper has oxidation state of plus 1, means 4s1 3d10 copper atom. So, it loses 1 electron from 4s, means it has again 3d10 configuration. d10 means all the d orbitals are fully filled, all the d orbitals are fully filled. So, no d-d transition is possible. If all the d orbitals are fully filled, electron will not go to any upper state because there is no room there. वहाँ पे कोई जगह है ही नहीं, तो इलेक्ट्रॉन कैसे जाएगा? इलेक्ट्रॉन नहीं जा सकता है. So, if he transition will not take place, then it is colorless, right? But CuCl2 Q plus cupric chloride is colored. Cupric chloride is colored because it has a d9 configuration, means here it has one half filled orbital. So, electron can move to this orbital by observing one radiation, and when it comes down to the ground state, it emits the radiation having complementary color and the substance looks always complementary color. Okay? Next, there are many species, very interesting, even with d0 configuration, they are also looking colored, with d0 configuration. Let us see some beautiful examples like potassium permanganate plus 7 oxidation state, means it has a d0, potassium dichromate, it has a d0 configuration plus 6, but it looks your violet color and it looks your orange color in these compounds. And also potassium chromate K2CrO4, it has also d0 configuration, it looks yellow, you see. Scandium chloride having d0 configuration is colorless, titanium dioxide having d0 is colorless, but here even if they have d0 configuration, still they are colored. what is the region. And also sodium vanadate Na3VO4, here it has also D0 configuration, it looks red color. Why? Because of a charge transfer phenomenon. How that charge transfer phenomenon takes place? Manganese, permanganate, you look into the permanganate, O minus double bond O. Here the electron, two electrons present on oxygen, when sunlight falls on this oxygen, this electron absorbs the radiation and undergo and pushes into the d orbital of manganese. It has a it has a +7 oxidation state, and on getting this electron, it now comes down to +6 oxidation state. When it returns back, when manganese returns back that electron, that reflected electron gives you violet color. This is called charge transfer phenomenon. Okay. So transition metals mostly for colored compounds, either in solid state or in a solution state. Remember, the 4 regions, there must be DD transition, and for DD transition, what you need is the complex or compound, transition metal complex or compound must have to have a D1 to D9 electrons, so that at least if one electron, unpaired electron is present, that will undergo transition. For a transition, unpaired electrons are necessary. If unpaired electrons are not present, it may be colorless, like D0 and D10. All zinc salts are colorless, So many times it has been asked in the examination, why? Because zinc has only one oxidation state, that is +2, 4s2 3d10. On losing 2 electrons, it has only 3d10 configuration, means 10 electrons are present in a 3d orbital. So since all the d orbitals are fully filled, there is no question of any transition. इलेक्ट्रॉन जाएगा तक जाएगा कहाँ जाएगा, वहाँ पे तो खाली जगह है ही नहीं. Since no transition is possible, so all zinc salts are colorless except if there is some crystal defect. Zinc oxide, you must have read it in a solid state. Zinc oxide, when heated, it looks yellow color, on cooling it looks white color, it is because of crystal defect. Second reason, even D0 configuration, D सबसेल में इलेक्ट्रॉन है ही नहीं, फिर भी they are looking colored like potassium permanganate, potassium dichromate. It is called charge transfer phenomenon. Here you see how in manganese, potassium permanganate, the electron present on oxygen O minus absorbs radiation and enters into the vacant d orbital and reduces its oxidation state from +7 to +6, and when it returns back, it reflects the energy and or transmits the energy that has a particular color. This is called charge transfer phenomenon, and for charge transfer phenomenon you need a D0 configuration. For the same reason, sodium vanadate, potassium chromate, potassium dichromate, they are looking all colored. Third reason is polarization of an ion. Polarization of an ion. Very interesting. So for polarization of an ion, and for this purpose, what you need is the central metal atom or ion must have D10 configuration. You see D10 इलेक्ट्रॉन हो के भी वो कलर फॉर्मेशन कर रहे हैं. How? It is because of a polarization of anion. For example, silver chloride, you must have heard silver chloride is colorless, but silver bromide is yellow color, pale yellow, and silver iodide is dark yellow. How? Silver, you know, silver kata oxidation state is +1, and copper, silver, gold, they belong to one group. So silver Ag plus means it has a D10 configuration, but it looks yellow color. Why and how? Because you see iodide I minus, the iodine has a larger size, I minus has a larger size and Ag plus. So it polarizes the electron cloud of anion polarizes the anion, the electron cloud of anion, that means Ag plus this electron cloud is polarized. So electron now, this is Ag, this is I. So its electron is polarized, and on observing the radiation, H nu from sunlight, on observing the radiation, it enters into the vacant d orbital of a silver cation. When it returns back, it emits the energy which looks your dark yellow color. So this is called polarization of anion. So if a cation is capable of polarizing anion, that means that electron will enter into its vacant orbital by observing one radiation, and when it will return back, it will emit the complementary colored radiation and the substance will look colored. But in case of silver chloride, silver is unable to polarize the chloride anion. No polarization, so no transfer of electron. So this is the third reason why the transition metal compounds are colored. Number one, DD transition. Where DD transition is not possible, maybe charge transfer phenomenon. Where charge transfer phenomenon is not possible, if it has D10 configuration, there may be polarization of anion. Similarly, PbCl2 is colorless, but PbI2 is colored. शायद ये बात आप सबकी समझ में आ चुका होगा. Perhaps all of you understood very well. PbI2 is colored, but PbCl2 is colorless. Similarly, mercurous chloride Hg2Cl2 is colorless. For same reason colorless, but Hgi2 is green colored. Same reason. This is nothing but your polarization of anion. Last one is your crystal defect. You must have read in solid state, the FeS2 is called fool's gold. It is called fool's gold. It looks like a gold. Fool's gold. Here it is due to crystal defect. And because of this reason, it looks golden yellow color, and people are getting fooled, just thinking that this is gold. Really, it is not gold. This is iron compound, and this color is created because of a crystal defect. And that crystal defect, you remember, it is called metal excess defect. Due to this reason, it looks full. It looks golden yellow color, right? Next important property is ability to form complex. Transition metals, this is most important property. They have capacity to form complex. What are complexes? Because it is associated with it has capacity to get itself associated with the number of ligands according to its coordination number or effective atomic number rule. You will read it in coordination chemistry. But remember, it is just like joint family. You know, the nucleus family and joint family. In a joint family, there is a guardian, head of the family, and that head of the family holds all the family members together. It is a complex family. It is not that easy for anyone to make a complex or joint family. So to make that complex, that metal, this transition metal plays important role. So in complex formation, transition metal plays vital role. Like in organic compound, carbon plays a central role. Here in complex formation, transition metal makes central role or plays a central role in making all complex compounds. Why? Because it has few unique characters, unique properties like small size, small atomic साइज. फैमिली के जो मुखिया होगा उसका अपना भी फैमिली है, परिवार है, वो छोटा होना चाहिए. Number 2, it must have a high nuclear charge. हेड ऑफ द फैमिली का कमाई भी ज़्यादा होना चाहिए. बड़े भैया महीने में 4 लाख 5 लाख रुपया कमाते हैं, तो obviously all the members of the family will definitely want to stay with him. Second reason, high nuclear charge होना जरूरी, means ये high charge density, means ये high phi means ये charge density, high charge density, चार्ज डेंसिटी हाई होना जरूरी है. थर्ड वन इज अवेलेबिलिटी ऑफ वैकेंट डी ऑर्बिटल्स. अवेलेबिलिटी ऑफ डी ऑर्बिटल्स बहुत ही कमरा है, रहने के लिए जगह की कोई कमी नहीं है. तो अगर ऐसी तरह पर्सनालिटी किसी का होगा तो नेचुरली वो जॉइंट फैमिली बना के ही रहेगा. ठीक है. सो दैट मीन्स सिमिलरली ट्रांजिशन मेटल हियर प्लेज वेरी वेरी वाइटल रोल इन मेकिंग ऑल कॉम्प्लेक्सेस बिकॉज ऑफ इट्स हाई चार्ज डेंसिटी, मीन्स स्मॉल साइज हाई न्यूक्लियर चार्ज and the d orbitals are vacant. So it can accommodate the electron pairs donated by different ligands. It can stabilize them, it can hold them together to make a complex molecule, right? Example, so many times it has been asked in the examination, give one amine complex of a copper. So many times this particular question has been asked. Give one amine complex of copper, you see CuNH3 whole 4 SO4. Remember this complex, what is its name? You will read it in coordination chemistry. Here it is tetraamine copper 2 sulfate. You see copper now holds 4 ammonia and 1 sulfate and makes this a beautiful blue colored complex. It has that capacity, that ability. Secondly, also one question was asked in the examination, give one amine complex of a silver. Give one amine complex of a silver like Ag, NH3 whole twice Cl. This is the amine complex of a silver. What is its name? Diamine, silver 1 chloride. Likewise, there are so many other complexes, you are well acquainted with them, you know them very well. K4, Fe, CnRO whole 6. It is called potassium ferrocyanide, or in IPC name hexacyanido, potassium, this is potassium hexacyanido ferrate 2. These are so many complexes, you know, biological complexes molecules like hemoglobin. Hemoglobin is the main component of a blood, and that is only made by ferrous iron. Ferrous iron is responsible for creation of a blood. That is a complex molecule. In you see in tree, in plants, the green pigment chlorophyll is a complex molecule made by magnesium. Of course, magnesium is not a transition metal, right? So transition metals have very very vital role. 99% complexes are only formed by transition metals, right? So next is your catalytic properties. Catalytic property, transition metals. What are catalysts? Catalysts are the chemical substances. Catalysts are the chemical substances added externally to a reaction to accelerate the speed or to increase the rate of reaction. To increase the rate of reaction or to decrease the rate of reaction. If any catalyst increases the rate of reaction, we call it a positive catalyst. If any catalyst decreases the rate of reaction, we call it a negative catalyst. That means catalyst is a chemical substance which alters the rate of reaction. Reaction का speed either बढ़ाएगी या कमाएगी. It will increase or decrease the speed of reaction. And most of the catalysts are nothing but transition metals and their compounds. One of the famous reaction, in oxygen family, you must have studied that in contact process, when we are manufacturing sulfuric acid, in contact process when we are manufacturing sulfuric acid, in first step it was your formation of a sulfur dioxide. Remember, sulfur, or you take any pyrite ore, on combustion produces sulfur dioxide. Second step was very, very important, conversion of a sulfur dioxide to sulfur trioxide. It was a great challenge because the reaction is exothermic and reversible. sulfur trioxide नहीं हो पा रहा था, तो in this situation vanadium pentoxide played important role. Vanadium, a transition metal, its oxide played very, very important role in making sulfur dioxide to sulfur trioxide. How? You just have a look into the mechanism. Sulfur dioxide plus half O2, vanadium pentoxide plays a vital role. It gives you sulfur trioxide. Sulfur trioxide, how? Sulfur dioxide, because vanadium pentoxide. Why vanadium pentoxide or why transition metal compounds act as a catalyst? What are the reasons? There are two reasons. Number one, they have variable valency, means they have number of unpaired d electrons. How these unpaired d electrons are responsible for catalytic property? Yes, these unpaired electrons absorb wide variety of radiations. They absorb wide variety of radiations and they supply to the reactants, and as activation energy, they provide this energy as activation energy, they activate them to react together. So that is why this is one of the important property. Here you see, that is why they participate in reaction and they make number of intermediates, unstable intermediates. These unstable intermediates are then converted into stable products. We will discuss in detail. Okay? So the catalytic property of a transition metal and their compounds are basically due to two reasons. Remember, due to two important reasons. Number one, they have variable oxidation state, means they have number of unpaired d electrons present, which these unpaired electrons they absorb radiation and they provide to the reactant and as activation energy and activate them to proceed the reaction further. Here vanadium pentoxide, you see, sulfur dioxide is oxidized to sulfur trioxide by vanadium pentoxide. These catalysts they form number of unstable intermediates. How? Sulfur dioxide, the two electrons are provided by vanadium pentoxide, one oxygen is provided by vanadium pentoxide. So it becomes sulfur trioxide, the reaction is reversible, and then plus it is converted to vanadium tetroxide, and vanadium tetroxide, this is intermediate, this is intermediate, this is intermediate, and vanadium tetroxide then absorbs oxygen from air and gets itself converted to vanadium pentoxide. Okay? So in this way it catalyzes the reaction. Another important thing, transition metals provide large surface area due to presence of their vacant orbital. उनके पास unpaired d electrons भी है, vacant d orbitals भी है. That vacant d orbital provides a large surface area to the gaseous reactants. They absorb the gaseous reactants on its surface and provide them activation energy and do the reaction. So how? You see, you must have had nitrogen plus hydrogen in Haber's process of a synthesis of ammonia. Here porous iron and molybdenum is your promoter and a porous iron is the catalyst. Here iron absorbs nitrogen and hydrogen on its surface and does the reaction to produce ammonia gas. Similarly, you see in potassium chlorate KClO3, if you heat it with in presence of a manganese dioxide or a pyrolusite, reaction becomes very fast to give you 2 KCl and a oxygen gas. And the very famous reaction, if you add any alkyne, do hydrogenation or reduction over a platinum or palladium or nickel surface. These transition metals, they observe the gaseous reactants on its surface because of a presence of d orbitals and provide them energy and do the reaction as they convert them into ethane. So this is called catalytic hydrogenation of alkynes or alkenes. All these processes you see, in almost all processes you see transition metal or its compound play important role in catalyzing the reactions because of these two unique properties. Variable valencies, variable oxidation states, or they have unpaired d electrons. They are responsible and they provide large surface area. Okay. Next is the alloy formation. It is another unique property because you see the transition metals, they do not differ from each other in their size, almost a similar size. That is why if you heat one transition metal and if you melt one transition metal and melt another transition metal, if you mix them together and freeze them, they will make an alloy. Our alloy is nothing but homogeneous mixture of two or more transition metals. How they do intermix with each other? Because of a similar atomic size. Because of similar atomic size, one atom can replace another atom in its crystal lattice. Means in copper lattice, zinc can be replaced, zinc can be placed, and also in zinc lattice copper can be placed. Because of a similar atomic size, they form alloy. You know the very famous alloy is your brass. Brass means it is the alloy of copper and zinc. Because of similar size, remember, for making alloy the metals must have to have similar size so that they can fit well into each other's lattice, right. Similarly, in case of bronze, you have copper and tin, almost a similar size. But you cannot mix copper with potassium or magnesium because they differ largely in their size, so they cannot make any alloys, right. So when metal is mixed with silver, is mercury, any alloy with mercury is called as amalgam. 1 year such type of question was asked, what is amalgam? It is the alloy of mercury, sodium amalgam, potassium amalgam, zinc amalgam. Okay? These are basically used as good reducing agents. So any alloy with mercury is called as amalgam, right. Next is your interstitial compound. Interstitial compound means you see in the transition metal crystals, there are many voids, many empty space are present. Interstitial site in their packing, you see there are interstitial sites like this. In this interstitial site, the small atoms like hydrogen, boron, carbon, nitrogen are trapped. They are trapped and they cannot go out of this place. So they are trapped and permanently trapped inside and they cannot go outside. So there is some force of attraction exists between the host. This is called host. Host means a transition metal and these are called a guest. So host plus a guest on combination, they make you interstitial compound. Interstitial compound. Interstitial compound. So these are non-stoichiometric compounds. There is no formula how many types of atoms will be entrapped in the crystal. So there is no formula, therefore they are called as non-stoichiometric compounds, right. So alloy formation and interstitial compound formation, these are the very important properties. Remember, for your examination point of view, CHE students, remember, you will be asked what are transition elements and discuss any 4 important properties. You must write variable oxidation state, colored compound formation, your catalytic property and your complex formation or alloy formation. These are the important properties you must have to write and many questions are likely to come from this section. So let us discuss what are the questions being asked in previous year examinations. You see, color transition metal is due to dash, DD transition, PP transition, paired electrons, none of these, DD transition. And what is the value of a spin only formula for Fe2 plus in 2018? It was asked in Fe2 plus means D6. D6 means you have to calculate, there are 4 unpaired electrons. Remember, you have to calculate a number of unpaired electrons. Since it is N, so value will be 4.90 bm. Remember the trick. Why do transition metal form complexes? Because of 3 reasons: small atomic size, high nuclear charge, and availability of vacant d orbitals. This question was asked in 2015 and 2002. And why do most of the transition metals compounds are colored? Because of a presence of unpaired d electrons. When that unpaired electron absorbs radiation from visible light and undergo d transition, and when it returns back, it emits the energy or radiation having complementary color, and substance looks complementary color. And write down formula of amine complex copper. Already I have discussed CuNH3 whole 4 SO4. Write the formula of amine complex of silver AgNH3 whole twice Cl. Why chromium has the highest boiling point than? Because chromium has the highest number of unpaired electrons, means 6 number of unpaired electrons, and it is capable of making more number of covalent bonds, which adds to the strength of a metallic bond. That is why it has the highest melting point among 3D series, right? Distinguish between alloy and amalgam. Amalgam is nothing but your alloy with mercury, and alloy is normal, is a molten mixture of any 2 metals except mercury, right? What are transition elements? Describe in 4 important properties. Already I have discussed. Again, at last I am telling you, transition metal D block elements are called as transition metals because 3 reasons. Number 1, their properties are intermediate between S block and P block elements. Number 2, both valence shell and nearest inner shells are incomplete, and they have partially filled d orbitals. So in this way, you will be asked questions in your CHEC examinations, I am sure. And part questions are also likely to come. Why transition metal compounds are paramagnetic? Or you may be given some compound like FeCl3. What is its magnetic moment? What is its magnetic moment? You have to write the number of electrons and then do the magnetic moment value, okay, using that trick and a formula. So I hope I am sure that you must have enjoyed the class. Whatever doubt, whatever fear was in your mind, it must have been cleared, and I am hopeful whatever questions are likely to come in your CHSE, CBSE or any other entrance examinations, you will absolutely find no difficulty in answering all these questions. So thank you all. God bless you. Okay, thank you.